All right, so welcome to our International Colour Day Forum on colour in relation to rendering artwork with lighting. Before we begin, I'd like to acknowledge the Gadigal people of the Eora Nation, the traditional custodians of the land we're speaking from, and to pay my respects to their elders past and present. Uh, this event continues a series of webinars organised and presented free of charge by the New South Wales Division of the Colour Society of Australia since 2020, and it is our second online forum presented jointly with the International Colour Association, or AIC, Study Group on Arts and Design. The first being our forum on the XRF revolution in painting analysis and painting conservation, held on International Colour Day last year. I'd like to thank Professor Maria João Durão, who is AIC President and Chair of the Study Group on Arts and Design, for her contribution to our ongoing forum series. As Chair of the Portuguese Colour Association, Maria João is also to be thanked for taking the proposal of International Colour Day to the General Assembly of the AIC Congress in 2008. If you looked at the email notice for this event or our recent posts on Facebook and Instagram, you'll have seen that there have been again many online events from around the world celebrating International Colour Day this year, including two that are still to come. From the Colour Group of Great Britain on the philosophy of colour on March 25, and from the AIC Study Group on environmental colour design on colour and freehand sketching of the built environment on March 27. And before we begin, let me also remind you to keep an eye out for coming events from the Colour Society of Australia, beginning with our next webinar on Sunday, April 19, on racism in colour theory with Edward R. Charbonneau of the Minneapolis College of Art and Design. We have a full house of 100 registrants today, so we're asking everyone to stay muted during the presentations. But if you have questions, please submit them in the chat and we'll get to as many as possible in the discussion at the end. I'll now introduce Vladi Rosolova, who has organised today's forum and who will be our host from this point on. Vladi Rosolova has more than 12 years' experience working as a lighting designer for leading lighting consultancies in Sydney and London, and more than 6 years of experience working in architectural offices in the Czech Republic and Australia. Her postgraduate study on illumination science at the University of Sydney in 2021 brought her interests in light and colour together in research focused on visual lighting phenomena in painted art, namely colour constancy, which was awarded the Phillips Prize for Illumination Science. Vladi has served on the committee of the New South Wales Division of the Colour Society of Australia for 2 years and was elected Secretary of the New South Wales Division at the end of last year. Vladi is also an organising member of Women in Lighting Sydney, part of a global initiative and digital platform spanning 70 countries that highlights and supports women working in the lighting industry. So I'll pass it over to you now, Vladi. Thank you. You're muted, Vladi.
Oh, thank you. Thank you. Good afternoon or morning or evening, noon or midnight, wherever you are in the world. We are very delighted to have audience from all around the globe, people joining us not only from Australia and New Zealand, but also from Portugal, Greece, England, Austria, Germany, Colorado, Holland, Finland, New York, Quebec, Tokyo, Chile, South Korea, Washington, Rio de Janeiro, Florida, Phoenix, Texas. Welcome. Or if you join us a little bit later. It is my pleasure to guide you through this panel and to introduce our today's speakers, my dear colleagues and friends and my fellows. You probably asked, why lighting? Why is it so important? Light is invisible, is not noticed, yet it is the most important part of how we display artwork. Lighting creates our experience of the artwork that we come to look at in the art galleries. Without good lighting, we would not be able to see colors of the art piece, its texture, form, and shape. And so each of our speakers today deals with lighting and the properties of light in either theoretical or practical way. They are all based here in Sydney in Australia. Rosa and Emrah are practicing lighting designers in the field of architecture, working for the highest regarded Australian lighting consultancies. Wenye and Emrah also explore lighting and color in the realm of science, which they also teach at the University of Sydney. And Leigh is a lighting technician in the Art Gallery New South Wales, dealing with the practical reality of working, of lighting artwork. And now how today's event is structured. I will introduce our speakers one by one before their talks. And after all the talks are finished, we will have time for questions and a discussion. And please, yeah, as David said, put your questions in the chat even throughout the event, and we will come back to them in the question time, or you can raise your hand during the question time and we will unmute you and you can ask via your video. So that was the organizational, and now let me introduce our first speaker, Rosa Arcaya. Rosa is a creative and strategic lighting designer and project leader. She has extensive experience delivering projects of a variety of scales and complexity, from master planning, large-scale commercial projects, boutique bars, private residences, even to art exhibition of 700 curated objects. She specializes in experience design for digital physical environments and the development of lighting schemes to create immersive atmosphere. Rosa's background is in design. She grew up in Spain, surrounded by a family of talented designers. She initially chose the path of interior design, which she studied and practiced in Barcelona. Her professional career in lighting started when she moved to Sydney in 2013. And during her time in Sydney, she completed her master's degree in illumination science at the University of Sydney, while she was working at the same time at one of the Sydney lighting practices and applying the theory and science into the practice. In 2017, she relocated to London, where she gained most of her experience in some of the highest regarded studios. And after 7 years being overseas, she brought the wealth of the experience back to Australia, and we are now delighted that she will share that part of this knowledge with us today. And now over to Rosa.
Thank you so much, Vladi. I'm going to share my screen. Just one sec. Let me just do that first. Okay, can everyone see a very colorful slide? Yeah, Vladi? Yeah. Right. Expanding on Vladi's introduction, we often talk about color as though it belongs to objects. Kiwis are green, strawberries are red, but in reality, there's no color without light. If you were going to switch the light off, the color disappears. And if you change the light, the color of that object changes. The same blue can appear deep and saturated, or dull and lifeless. Skin tones can glow or turn gray. So tonight I'm going to talk about color, but through the lens of light. Welcome to my talk on TM30, a new, not so new, standard for evaluating color rendering. My talk tonight will be a bit technical, but it will set you up well for Wenye's and Emrah's talks, providing a baseline to understand the principles of color rendering. My name is Rosa, and as Vladi said, I am a lighting designer. I work with interior designers and architects using light to shape the right atmosphere for spaces. I also studied colorimetry as part of my master's at Sydney Uni. And as part of preparing my talk this evening, it's been quite fun to review some of my old notes from that course and put this presentation together. So I hope you all enjoy it. So take a moment to review the graphs and the balloons on this slide. On the left, we have the theoretically perfect light, equal energy across all the wavelengths, with 3 balloons below, showing the 3 primary colors as we expect to see them. We've got the red, the green, and the yellow. On the right, we have a light with only blue and yellow wavelengths. When exposed to over the 3 balloons on the right, this light only reproduces, well, on the balloons on the left, this light only reproduces those 2 colors. So our red balloon appears brown and our green balloon appears gray. But why should we care about color rendering? In our day-to-day, we are surrounded by a range of different light sources: daylight, incandescent lights, fluorescence, good LEDs, bad LEDs, and these lights all have an impact on the color of the objects that we see. And that's exactly why we should all care about color rendering. As professionals in the color industry, everyone in this call, we are all familiar with color scales. But what some of you might have never stopped to realize is that these color scales assume a specific light as a reference illuminant under which all the colors in that scale are defined and measured. The Munsell color system on the left was developed in the early 20th century by Albert Munsell, who needed a system to describe color based on how humans actually perceive differences in color. And it is still widely used today. Originally, the system used a legacy approximation of daylight as the reference illuminant under which these colors were defined. How do we then quantify or measure these different light sources to ensure that the reference illuminant is for you and for me is the same when we do these color tests? So introducing the SPD. SPD stands for spectral power distribution, and it describes how much power or energy a light source emits at each wavelength across the visible spectrum. In other words, an SPD shows how much light is present at each color of the rainbow. As you can see on the slide, daylight has a relatively smooth and balanced SPD, meaning it contains energy across most visible wavelengths. Incandescent lights have a continuous SPD, but their spectrum contains lots of energy on longer wavelengths, reds and oranges. Fluorescent light sources have a discontinuous or spiky SPDs with lots of energy at points along the spectrum, like in purples, blues, green in this graph. This is partially as a result of their design objective as an energy-efficient light source. So when I say reference illuminant or perfect light, you might think it would be a light with an SPD like you can see on the left, with equal energy across the visible spectrum. But that fails to take into account our complex visual system, which has evolved with firelight and daylight, and as a result, it doesn't perceive colors equally. So an equal energy SPD, a theoretically perfect spectrum, would actually produce the perception of unnatural colors that our visual system rarely experiences. Bearing in mind that complexity, what should we use then as a reference to define the perfect source for color reproduction? So today, the most common references are the illuminants established by the CIA, the International Commission of Illumination. And there are a few depending on the application. The 2 most commonly used are Illuminant A, which represents an incandescent or halogen light with a color temperature of around 2800 Kelvin, and illuminant D65, which represents daylight with a color temperature of approximately 6500 Kelvin. We tend to use illuminant A in color science and most lighting measurements, with illuminant D65 being commonly used in photography, digital imaging, and printed media. But there are a few others that can be used as well. The standard illuminants take into account both the energy and the I to arrive to the ideal reference sources. Bringing all these together, the way we perceive color is then a combination of three things: the light itself and its spectral power distribution, the properties of the object, its reflectance, and the reflected light, which is then captured by our eye or a measuring device. So in other words, perception is understood as the reflected color detected by our eye, which is a combination of the energy of the light and the reflectance of the sample, of the energy reflected of the sample. This illustration wants to demonstrate how three different lights render the same skin tone completely different. The energy of the light on the left, combined with the reflectance of the skin, which is common for the three examples, equals the reflected energy. So let's look at the first example. In the first example, we have a cool white light. It's a fluorescent light in this case, with high energy in the blues and a peak towards the greenish yellow part of the spectrum before dropping into the reds. The skin is actually quite dominated by the reddish tones. So the result is a reflected color with a peak on the greens and yellows, and the reds have almost disappeared. In the other two examples, where the reflected SPD is very much a combination of the light, in the other two examples, you can see that the reflected SPD is very much a combination of the light and the reference factor of the skin. So now we understand the impact of light on color. Let's move on to color rendering. Color rendering is the comparison of a test source to a reference source that is considered to have the ideal rendering qualities. What we're going to see in this presentation is how this comparison is done and how to understand the data that we get out of it. In the 1960s, fluorescent lighting was becoming widespread. These new light sources were very energy efficient, but often made colors look unnatural. The industry needed a way to measure and compare color rendering performance of these lights. As a result, the industry developed CRI, a method created by the CIE and first published in 1965. So CRI stands for Color Rendering Index. This system aims to quantify how accurately a light source reproduces color. CRI provides two reference illuminants to choose from, based on the color temperature of the light you are testing. This is done because matching the color temperature makes it easier to then evaluate the differences in the spectral shape of the lights themselves. So sources below 5000 Kelvin are compared to an incandescent light. And sources above 5000 Kelvin are compared to daylight. So a reference such as the CIE standard illuminant D65. CRI uses 8 color samples. However, over time and in some regions or applications, extra colors have been added in search for more precision. CRI gives us one single score. This score is from 0 to 100. When CRI is 100 is when the light matches the reference source accurately across the 8 color samples that we've seen before. Now, while CRI has served us well over the years, it has a number of problems or deficits. And here's an example. This is a neodymium light, which is a halogen lamp that has a special coating designed to alter the spectrum and filter the yellow and green wavelengths, as you can see in the SPD. This light gives a purer, more like sunlight with enhanced pinks and reds, and is used to pleasantly render skin tones, some painted surfaces, and retail environments. But as you can see, this light is getting a terrible CRI result score of 77. This is just because it's making some colors look more vibrant in the 8 color reference samples. The opposite problem also exists. As CRI reference color samples are dominated by pastel colors, strong colors like deep reds or deep blues aren't tested. That means that those colors may look dull under very high scoring light. The fact that only 8 color samples are tested also means that narrowband SPDs can achieve very high scores if they coincide with the 8 reference colors of CRI, while other colors will look wrong. Lastly, because we only really get one number as an average result, means that good and badly rendered colors cancel each other out to produce one number that hides what the actual problem is. So the lack of preciseness in this system started creating some issues. Manufacturers are finding ways to trick the system and create sources that get very high CRI scores, but in practice don't render the full spectrum well. If there are any lighting designers in this call, they'll know what I'm talking about. And it feels like these days all LEDs have a score CRI above 90. So this is what takes us to the need of creating a new, more accurate system to compare a test source with a reference source. As I mentioned earlier, CRI was originally developed to evaluate fluorescent lamps, so it doesn't fully reflect the requirements we have now for assessing the color rendering of LED lighting. So this is how TM30 was born. TM30 was created by the IES, Illuminating Engineering Society, in 2015. So more than 10 years ago now. Unlike traditional CRI, TM30 uses 99 color samples chosen to represent real-world colors, giving a more practical and accurate assessment. Each color sample is scored from 0 to 100, and the average of these results gives us the fidelity score, or RF. RF shows how similar the 99 color samples appear under the test light compared to a reference light with the same color temperature, as we said before. RF scores are often similar to CRI, but sometimes they differ. This is because some light sources have been designed to perform well under the CRI test, yet many miss colors that TM30 evaluates. While RF tells us how accurate colors are, it doesn't tell us whether colors appear more or less saturated. This is why TM30 also includes the gamut score, or RG. RG represents the average change in color saturation compared to the reference light, like as always. Results over 100 mean that the test source is more saturated or vivid. Results under 100 mean that colors appear less saturated or more muted. For example, a light source might have a high RF, meaning the colors are fairly accurate, but still have an RG above 100 and making those objects appear slightly more red or more green, because some parts of the spectrum are stronger, like the neodymium bulb I mentioned earlier. RG, then the gamma score, is an average value, so it tells us the overall saturation change, but not which specific colors are affected. The last piece of the puzzle then is the color vector graphic. This diagram in TM30 has the average results of RF and RG at the top and the color temperature on the bottom left. The diagram always shows a black line for the reference illuminator, and then we've got arrows and we've got a red line, which references the test source, the source we're testing. Now, the arrows are related to the RF, the hue shifts or color shifts, if you like. When they are pointing straight to the middle, it means that they are very accurate on that color. But when the arrow is pointing another direction, it means that that color is shifting towards the color pointed at. For the RG or chroma, color saturation shifts, if you like, we need to look at the red line. When the red line or the test source line is inside the reference line, we've got an area of undersaturation. When it's outside the black line, there is an area of oversaturation. So in this diagram, it's not a great example. What we can see is an LED source with a very good color rendering. So let's look at some other examples. I have extracted this information from a spreadsheet that Wenye sent me a couple of weeks ago that calculates the TM30 and CRI by just introducing the SPD information of a light source. So let's have a look at this example, which is a neodymium bulb, like we mentioned earlier when we were explaining the CRI. This is a warm halogen lamp with a color temperature of 2756 Kelvin. It has a color fidelity score, or RF, of 87 and a gamma score of 109. Looking at the color vector graphic, you can see that the colors that are oversaturated are the pinks and the cyans, which is what creates that oversaturated daylight-like appearance that made this light popular in retail and for skin color rendering. But the CRI is 77, which is a very low result for a desirable light bulb. Now let's look at a fluorescent light. This one has a color temperature of 6,425 Kelvin. So the reference is not the Planckian locus like it was before. The reference source is a daylight source reference. So you can see the reference source in black up in the SPD graph. It has a color fidelity score of RF 81 and a gamma score of RG 90. As you can see in the color vector graphic, this light undersaturates most colors, except from some yellowish greens and some violets. This also has a considerable color shift, especially in the oranges, as you can see this pointing towards that side, and the violets, the arrow pointing towards the blues or the purples. Lastly, let's have a look at an LED light source that actually scores quite well under CRI. As you can see, this light is CRI 90. This light has a color fidelity score under TM30 of 86 and a gamma score of 104. With a CRI of 90, this light would be considered exceptional for most applications. But TM30 tells us the full story in the color vector graphic. So let's have a look. This LED has an RF a little bit, so the RF score is scored, sorry, this LED has a poorer RF than the CRI results against the 99 color samples at 86, as I said, and it oversaturates some colors, particularly the greens, which is never a desirable trait in lighting. To get these results, we can also use a device called a spectroradiometer. You can take this device, point at a source, and what this device essentially does is it splits the light into its individual wavelengths, and it gives you the full CRI and TM30 data. They're quite expensive as they are little complex devices. So TM30 has long suffered from a lack of understanding in the industry, limiting its impact. But now that we understand it and have the tools that make it quick and efficient to use, let's embrace TM30 so we can make better lighting choices that really bring artwork, colors, and spaces to life. I'll give you a couple of examples. Say you are the owner of a meat shop and want a good color quality LED that renders all colors really well, but you want an LED that oversaturates the reds to make the meat look fresher. Or you work at a gallery and they have given you a light with great color rendering, but it oversaturates the reds. And the creator says that the colors look too vibrant. Well, now you look at the data and you'll be able to understand why that light is oversaturating that particular artwork. So I hope this presentation has shown why color rendering matters and why the use of TM30 will help us pick and evaluate light sources more thoughtfully. Thank you.
Thank you very much, Rosa. That was amazing. Thank you. And I would like to now introduce the next speaker. Now, when we've got the theoretical understanding of TM30 and all the spectra of lights and the quality of rendering. So our next speaker is Dr. Wenye Hu. Dr. Wenye Hu leads the lighting lab at the University of Sydney and serves as the stream director of the illumination design program. She holds a PhD from the University of Sydney and a bachelor's degree in illuminating engineering from Fudan University. Before entering academia, Dr. Hu spent over a decade in professional lighting design, contributing to many projects, including the stadium lighting for the Beijing Olympics and the lighting design for the Shanghai Tower. Dr. Hu's research is focusing on AR-assisted lighting control systems, lighting for aged care environments, and sustainable road lighting. Her work has been recognized through competitive government-funded initiatives, including grants from the Australian Research Council and the US Government of Energy, where she collaborated with international research teams. She has been exploring spectral optimization, color science, and algorithmic modeling tune lighting systems to enable reconstruction of the visual environment and color appearance envisioned by artists. Most recently, she's leading a project supported by the Australian Department of Infrastructure, Transport, Regional Development, Communications and the Arts that investigates road pavement reflectance to improve lighting uniformity and enhance road safety. So I'll give now space to Wenye. Thank you.
Thank you, Vladi. And also thank you, Rosa, for introducing in great detail about the SPD and the CRI and also TM30. Now let's share my screen. Can you guys all see my screen?
Yep.
Okay, yeah, okay, good. Thank you. Okay, so my name is Wenye Hu. You can actually call me Dr. Hu because I'm the Dr. Hu in lighting. As Vladi just introduced, I worked for the University of Sydney. And today it's my great pleasure to have this opportunity to share some of our existing research and also some very early stage research we conducted in our lighting lab regarding the museum lighting. As you can see, the title of my talk today is the spectrum intelligence. And illuminating the colors of art. So the term spectrum intelligence is also being used in the other field with a different definition. But I borrow this term to here in order to refer to a combination of the spectrum optimization and also AI, the artificial intelligence. Because I'd like to talk a little bit like how in the future AI can help us in the museum lighting. Let's start by thinking about the lighting environment when those artists first created their artwork at that moment, and also the lighting environment today when we view the artwork when we're in the museum. I tend to call them the lighting then and the lighting now. As you probably know, a lot of historical paintings was created under the lighting environment, which is very different from what we experience today. Of course, today it's difficult for us to say exactly what kind of lighting environment those artists experience, but we can still make some informed assumption based on the historical context and also the artwork itself. For example, this very famous painting, The Girl Reading a Letter at an Open Window, which was created by Vermeer a long time ago. But from the artwork, you can see the artist probably created this painting in his studio under the daylight, and more specifically, probably under the daylight from the very small window. A lot of artists also like to create the artwork under the daylight. For example, Water Lily, like the whole series of Water Lily, Monet just tried to capture the very subtle variations of color and the light under the natural daylight. And then in this painting, Vincent van Gogh uses the light, which is a combination of the gas light in this restaurant and also some light in the evening, like the natural light in the evening. And in his letter sent to his sister, he mentioned he really enjoyed the experience to create this artwork on site, like in this restaurant. Some even early like paintings was created maybe under the candlelight or oil light or maybe even the gas light. So this brings to a problem, which is a good problem and a modern problem. And so that is a fundamental mismatch between the two lighting conditions, like the lighting condition when the artist created the artwork and also the lighting condition today when we view those artwork. And as a result, so the color we see today in the modern museum may not actually reflect what the artist experienced like originally. So this is one kind of color mismatch in the museum, but we also have another kind of color shift in the museum. Because this kind of color shift is usually due to the artist's age division systems. And the artists, also including ourselves, when we are older, like than 65, we started to experience some changes in our like visual systems, which means those age-related change, including something like the lens yellowing and also some diseases like cataracts, they all impact our visual systems. It will change our perception of brightness, of color, and also our sensitivity to the contrast. For example, Monet is another like a famous example. So at the very early stage of his life, he developed a very serious cataract. And then he went to Paris to receive some surgery. Because it's too risky to take the surgery on both of his eye, so he only did the surgery on one of his eye. And then after the surgery, his two eyes, like he experienced completely different color vision between the two eyes. And this kind of struggle actually strongly influenced his art style and also the use of color at the later stage of his artwork, like of the artwork at the later stage of his life. His example is quite famous, so I don't want to discuss it in too much detail. But today, I'd like to show you another very interesting example. So if you look at these two paintings here, you probably feel they are very similar, right? So both of them were created by a very famous Irish painter whose name is William Vladi. And the first one, this one, is created in 1836. So when this artist is in his 50s. And the second one is created when this artist is in his 70s. If you compare these two paintings, you probably will say, oh, the composition is very similar. The use of color, the arrangement, and even the facial expression of these two lovely babies are so similar. But what's the biggest difference between these two paintings? So you probably will say this one is more yellowish, right? Like the second one is more yellowish. So this one, according to some existing research, so the literature, they suggest this color shift is actually due to the artist's aged vision, because when we age, like our visual systems is dimmer, and then everything just covered with a yellow tint. And another kind of color difference or color shift in the museum actually caused by the pigment degradation. So a lot of historical pigments, some like the red pigment and also zinc, the ink yellow, they are not chemically stable. So once they are exposed to the light and also to the oxygen and also to like the environmental pollutants, so they will change the color. This is another very famous painting, which is a good example. So this is the irises, which was created by Vincent van Gogh a lot of years ago. So I downloaded this digital copy from the Getty Center. As you can see, the color of those irises, like most of the irises here are blue, except this one. The white one here, according to some scholars, they believe this is actually a representation of the artist himself. It's kind of isolated from the others. And all the other irises are blue for the current status. So this one is the one I downloaded from Getty Center. So I hope it can more accurately to represent the true color of the painting at this stage. However, according to existing literature, the color of the irises of those flowers shouldn't be blue. For the original copy, so they should be more purplish, something like this. And this picture here, this figure here, is something we created, like we edited the original. Sorry, not the original copy. We edited the digital copy of the original one, and we added the color to make it more purplish, as you can see here. And the reason those irises changed from purple to blue is also due to the pigment degradation. And here the red pigment is faded faster than the other pigment, and they are like also less stable than the other pigment. So the color started faded from the purple to blue. So they changed from purple to blue. let's just say if we understand all those color difference, color shifts in the museum, and if we rethink of the museum lighting in the future, so what we can get maybe a ideal lighting environment. Of course, we will we'll still say the conservation is the most important thing. It's our top priority. So a lot of research group has previously done a lot of research to study how to design the spectrum of light and to reduce the light absorption and also to suppress some specific wavelengths which associate with the degradation, like the pigment degradation. And then regarding the lighting design, we probably will focus a little bit more on the visual environment, the color perception. So we need to consider when people move from like one space to another space and how to adjust the visual adaptation, and also how those background will lead to the impact, will impact our perception of colors. If we look at a dynamic lighting environment, technically speaking, it's not difficult to create the spectral variations and to reflect the different color shifts during the daylight. We can also set up some different mode to create a kind of historical lighting environment for the viewer. But what I will suggest probably in the future with the help of AI, we can actually design the spectrum for specific material and also to consider the sensitivity of the pigment and also the color, which in terms of the spectrum reflectance of the painting. And in the future, maybe to design the lighting or the spectrum for individual artwork instead of just a cookie cutter solution. And then people may start to think, so does that mean if we aim to reconstruct the artist's previous experience, so does that mean we just use the exact SPD? For example, we just use daylight, or maybe we use the full spectrum LED, which is very popular in the market. A quick answer is no. There are two main reasons. One reason is the more light, like a daylight, and also the more broader light spectrum actually increases the risk of the damage, the light damage to the artwork. Another reason is they are not energy efficient. For example, full spectrum LED is very inefficient. But the most important thing is it's not necessary at all. And why it's not necessary at all, because it comes to our visual systems, like how our visual systems works and how we perceive color. As Rosa just introduced, like in our visual systems, we have three different types of cones. So basically, this image here is a color enhanced image to show our rods and the cones. So we have three different type of cones, which are the S cones. They are most sensitive to the short wavelengths, M cones sensitive to the medium wavelengths, and the L cones sensitive to the longer one. Each of them, they absorb the light, and then they send the information as the output of one channel and send the information to our brain. And after that, our brain started to compare the result and also to calculate the result, and then we perceive the color. So in our visual science, in our visual systems, there is a phenomenon called metamerism. So metamerism is a direct result of the principle of univariance. So the word univariance here is very good because it basically introduces what is this principle. If you look at this word univariance, uni here refers to means one, like the same thing. Variance means different thing. And the principle of univariance tells us even the spectrum are different, like a different spectrum distribution, they can still give us the same neuron responses in our brain and also in our visual systems. That will result in the exact same perceived color. Simply speaking, that means different spectrum can give us exact same perceived color. And then it's perfect for us as the lighting designer because it tells us the lighting can actually be designed in a way to make the light appear like the daylight, but we don't need to reproduce the whole spectrum, the whole daylight spectrum. It also enables us to do some optimization to reduce the unnecessary spectrum content, but at the same time, we still maintain the same visual fidelity and also maintain the constant color perception. And then how to do that? Because it sounds very complicated. So for example, if we look at this image here, as you can see, we have the optimized light with a kind of optimized SPD. So currently in most of the museum, I think they are using the phosphor converted LED. So phosphor converted LED is the one way to create the white light. Phosphor converted here means the light comes from the LED chip itself is blue light. And then we cover the blue light with some phosphor to convert the blue light to yellow light. And then we mix the blue and yellow together to create white light. So this is one way to create the white light. Another way to do that is to use the color mixing method, the multiple color mixing LED. And in the industry, we have, because we need at least 3 channels, red, green, and blue, to create white light. But in the industry, we also have maybe 5 channels and up to 7 channels LED. The one we use in our lighting lab is a 5-channel LED. So if we say 5 channels, and each of the channel refers to one single color, and then we can adjust each of the single color adjust the intensity of each of the single colored light into 255 different levels. And when we combine 5 channels together, that means we can create millions of different SPDs, right? And among these millions of SPD options, we can actually find a group of SPD which has the exact same perceived color of the daylight. And within this group, we can find an even smaller group who can give us also exact the same perceived color of the object, which is the painting. So for example, here we can find an optimized light, and it looks exactly like the color appearance of the light itself, looks exactly like the daylight. And when we use the optimized SPD to light up the artwork, the perceived color of the artwork also looks exactly the same with the one illuminated by the daylight. So if we can achieve that, that means we find an optimal SPD to mimic the daylight, but without creating the full spectrum of daylight. So the next question is, it sounds like we need to pick up the best one from millions of options. Of course, the human can't do that, but AI can help us to do that. So in our research, we use the optimization algorithm and also unsupervised machine learning method to find the best solution. So if we think in the future how AI can help us, I'd like to summarize it into 3 directions. So the first direction is a very established research field. My previous colleague, Alper Dumas, has done a lot of research on this, so I put his paper here. And in this direction, we can optimize the SPD in order to minimize the light absorption, and then we can protect the painting, protect the artwork. Another direction is to reconstruct the visual experience and reconstruct the color. For example, we can dynamically change the lighting conditions to mimic the color shift, the chromatic shift of daylight. And more complicatedly, we can also selectively to enhance some of the wavelengths or suppress some specific wavelengths to restore the perceived color balance of the degraded paint. For example, if the paint, the red component has faded a lot, so we can use the light to enhance the color. And the third direction is the I would like to call it as the composition mode, which means we can design a SPD to compensate the effect of the artist's visual impairment. We can also design a very specific light settings to allow the viewer to experience the artist's visual experience. So what we are trying to do is with the help of AI to create a light recipe for each of the individual artwork. And then people may ask, however, like all the painting, like none of the painting is just one color. So painting has so many colors, and how do you do this? Which means we need to do a lot of analysis of the color on the painting. So this one is what we have done currently in our lab. As you can see, the color has been edited to be more purplish. If I enlarge this part, as you can see, there are a lot of like black circles. We did the measurement to use our spectrum photometer to measure the spectrum reflectance of the small area. And after we did all the measurement, as you can see the result here, we collected the measurement for more than 200 different points. And then we put this data set into our optimization algorithm, and then we calculated to get our best SPD. Of course, we very soon we noticed it's actually impossible, not very practical to do the manual measurement for more than 200 for over 200 times on each painting. So we started to understand if we can do this digitally. And here we just write up MATLAB code to help us analyze the colors in this painting. So the method we use is called the unsupervised machine learning color cluttering method. Unsupervised machine learning is a very classic algorithm which used to identify the patterns of the large data set without the predefined labels. So we are not supervising the machine. We just allow the machine itself to learn the pattern from the large samples. And the painting we choose for this specific task here, as you can see, which is the background. So this is the Sunday afternoon on the island of La Grande Jatte, which was created by George Schuler. And this painting is a pioneer work of the pointillism. If you have seen this painting before, you probably know they use a very specific technique on this painting because they mix the color using a lot of small colorful dots. Instead of mix the pigment, for example, if you want to create, let's say, if you want to create, let's say, orange, you may mix the red pigment and also the yellow pigment in order to create orange, and then you apply the orange pigment, the paint, on the canvas. However, instead of do that, what Schuler did is he put a lot of red dots and then combine it with yellow dots. So for our visual experience, when we look at this painting from a distance, our brain can start to mix the color together to create orange. This painting is also one of his visual experiments. We selected this painting because there are a lot of small dots, which means there's no very large color block on this painting. And it also means if we want to analyze something to understand the color on the painting, this one requires a very high resolution. So we use this one to help us to decide the resolution. And here is the MATLAB code we use to analyze this painting. As you can see, once we start this program, it takes very quick to help us get the result. But it depends on the resolution. Currently, we set the resolution to be relatively low, and it only takes us 21 seconds to get a result. This is a recording of the analysis, and I didn't speed it up. So as you can see, just 21 seconds, and then we get the result. So if we look at the result here, you can see this one tells us where we pick up those color dots. And the program can help us to analyze the distribution on the CIE lab, CIE lab color space. And the most important thing is here, it also helps us to analyze the area of each color in order to understand the priority of those colors. For example, this one here tells us this kind of green is yellow or yellow is green actually occupied nearly 18.6% of the whole painting. And we sort the area from the largest to the shortest, which is from the smallest, the largest to the smallest, which is here. So the smallest would be this kind of purple, and that occupied about 8.8% of this painting. We need those information in order to set up the priority of the colors when we do the optimization. We also tried this on another painting, which is water lily, but kind of another version of water lily. As you can see, the colors on this painting is very similar, so it ended up with categories the color in just 4 categories. And once we get those analysis results, so we can put this as an input in our spectrum optimization program. Optimization problem in computer science is a very classic problem, and that means we use a computational algorithm to find the near optimal solution among millions of possibilities within the given constraints. Our input here is the SPD for each of the color channels for that luminaire. If this luminaire have 5 channels, we need to measure the SPD independently for each of the channel and use that as one of the input. And another input is the spectrum reflectance data, like the color of the painting. It doesn't matter if it comes from the manual measurement or comes from the digital analysis, so it can also be used as one of the input. And then the optimization objective. So one of the optimization objective we are currently using is the smallest color difference. And the color difference here refers to if we analyze the color of the painting illuminated by a reference source, and then we compare it with the color of this painting illuminated by our designed SPD. So what's the difference between these two? And then in the optimization objective, we aimed to find the smallest color difference. Mathematically can be expressed as the delta E2000. And the other things we need to set up for this program is to define the optimization constraints. For example, what's the difference between the reference light and the designed light? The reference light here, if you wanted to choose maybe the daylight, like you want to mimic the color of daylight, so reference light is daylight, the daylight spectrum. And if it's a candle light, you can also change the reference light. So we set the color difference to be here of the light to be less than 2 JND. So this is something basically very small difference, like kind of the threshold between noticeable or unnoticeable difference. The mathematical equation is using the delta U prime V prime, which is the coordinate in the CIE 1976 color space. And then we also look at the TM30. As Rosa has already suggested, the TM30 is a much better evaluation system compared to the CRI, the color rendering index. So here we set up the RF and RG. You can also define the range of CCT. So once we set up everything here, we just click the button, wait for a few minutes, and then the magic is done. So we get our best SPD. For example, this SPD here is the one we designed for that irises. Okay, so to conclude my talk, so in the future, if we have the chance maybe to reimagine the museum lighting, we hope the museum lighting can have more spectral intelligence, and maybe we can provide the light recipe for each of the individual artwork with the help of AI. This is the end of my talk, and I specifically wanted to say thank you to my PhD student Wen Bian, who helped me to edit the slides, which make it pretty, and also my previous colleague Alp and my previous PhD supervisor Wendy Davis for the research inspiration and also guidance. And also thank you everyone for your time and attention.
Thank you very much, Wenye. This was amazing. Wow, this is a really interesting research.
Thank you, Vladi.
Thank you for that. It's very inspirational. And yeah, we'll now move to our third speaker, Dr. Emrah Baki Ulas. Dr. Emrah is an international acclaimed lighting designer, speaker, and educator whose work spans the intersections of light, color, perception, and the built environment. Following an engineering degree at Theatrical Lighting Studies in Bogazici University in Istanbul, Turkey, he obtained a master's degree in architectural lighting design at the University of Wismar, Germany, and then his PhD at the University of Technology, Sydney, for his thesis, Casting a New Light on Museums and Galleries Towards Modern Industry Guidelines for Lighting in Museums and Galleries. Emrah is an associate professor of practice in the School of Architecture, Design and Planning at the University of Sydney. As technical director at Steenson Warming in Sydney, Emrah has contributed to many cultural, civic, and public projects. He brings a unique voice to conversations about light, art, and science. Emrah holds many recognitions from the lighting industry. His projects portfolio has an emphasis on cultural institutions, particularly museums and galleries. He contributed to numerous professional lighting forums around the globe. His work has been published internationally. So I'll hand over to Emrah now.
Thank you very much, Vladi. Let me just share my screen. One moment. I'll stop share for a second. Can you see the full page slide, or do you see it?
Yes, we can see the full page.
Full page slide. Okay, wonderful. Thank you. Sorry for those few moments. Great to be here. Thank you, first of all, yes, Vladi and David for the invitation, and also thanks to Rosa and Wenye and Leigh to come, of course, for their insights. And happy Color Day, everyone. I'm joining you from Camaragal land today. I acknowledge that I'm on Aboriginal country and pay my respects to elders past and present and emerging. But talking of color and light, it's also a night country. I also pay my respects to the skies, not only to the land, to the spirits. Now, like Rosa's and Vanya's talk, my talk today is also a relatively technical one, but it's a Sunday afternoon here in Sydney, of course. With your permission, I'll try to start with a bit of a personal reflection, if that's okay, and make it a bit more like a chat, hopefully. I've been quite fortunate, really, working on cultural projects over a number of years with curators, facilities people, technicians, conservators, and it's really amazing to work with people with so much sophistication, so much intelligence, so much knowledge. And with that comes a lot of complications and politics as well. Often museums and art galleries, it's always good fun. I think as a lighting designer, I see lighting art, especially in an art gallery context, is almost like preparing food in a fine dining restaurant context where, some might see it quite wasteful, non-essential, luxury, but these finer things make impact on people, and really these experiences play a big role in shaping us humans. But as lighting designers, we have this incredible job to make it taste good visually and memorable. It's a very privileged position to work on projects like that. But also, of course, it's quite different, museums, galleries, to fine dining restaurants, because in a way, our customers are not only today's people, but future generations, people that we'll never meet. So this topic of conservation, looking after artworks, is quite central to what we do, because what we deal with cause damage. We know that to many different kinds of materials, cause decomposition, degradation of materials, and so on. So we do apply limits to light exposure, sensitivity of materials. So that's the central kind of topic of my talk. And the lights that we use to light art are evolving. So the guidelines we use also need to progress. So the key message I'd like to bring in is to highlight basically some of the major issues about common practice around conservation, even in some of the most sophisticated contexts in museums and art galleries. And there's certainly more that we know that we need to learn. And our methods for managing light exposure has big approximations and a lot of guesswork within. And it's not to say, of course, there's a lot of knowledge on this topic over a lot of time that has been accumulated. So let me delve a little bit into it. So law of reciprocity is what we use very broadly and very kind of simply. If we look at this issue of light-induced damage, we basically multiply time and exposure, and that gives us what we call a kilo lux hour type of measure. And the convention in the conservation world is, of course, to use ISO blue wool scale. It's a standard to enable a comparison of different materials in terms of their fading potential, in terms of light damage. Now, blue wool 1 is the most responsive to light, the one that you see at the bottom of the page, goes all the way up to blue wool 8 scale, which is the least sensitive to light. And then there are types of materials that have no sensitivity to light as well. So the convention for many years, many decades, have been classified these in 3 categories: 1 to 3, blue wool 1 to 3 being highly responsive, and then 4 to 6 being medium, and 7 to 8 being low sensitivity materials. Now, when we look at the CIE guidelines on this, again, which existed for many, many years now, and this is more or less what you find anywhere in the world in museums and galleries, with some differences here and there. Broadly, what we find is that for objects, for artworks, for collections that are highly responsive, we have a yearly limit of 15,000 lux hours. And then it goes up to 150,000 and 600,000 lux hours per year. And these are like budgets. Some museums can spend them by limiting light exposure, like duration or the lux levels. What I found interesting over the years is that a lot of the time this is dumbed down to these numbers, 200 lux and 50 lux being the numbers that we look for. Again, art world, art galleries, museums are already quite, very tight in terms of resources. There's only that much effort and resourcing that can be put into looking at each and every artwork. I guess the kind of things that Wenye was talking on earlier, amazing if we were able to actually apply those methods into protecting, looking after each and every different type of artwork. Often it's really not possible, unfortunately. So anyway, we measure lux levels, 50 lux being the minimum one, 200 being the maximum for most sensitive objects. What for some years bothered me as a lighting designer was just looking at that R2 versus R3. In one instance, we have an annual limit of 150,000 lux per year, and in the other one, it's only 15,000 lux per year. But in both instances, we insist on 50 lux as being the minimum requirement to light artworks. And this comes from, again, guidance that 50 lux is thought of as the minimum light level we need in most instances to be able to recognize colors well, details well. So this is something that we've been questioning over the years. And really, reasoning tells us that that could be debatable. So when you look at artworks in different instances, we light them in galleries that might have white backgrounds. You have a certain lux level. You have instances where you have darker backgrounds, darker materials, less reflections. The eye's ability to adjust to light levels are very different. Our ability to see color in those two different extremes quite different, even in the same space as in similar to these projects, where if we light the space more generally, or if we deduct the light in general circulation, or even if we put the emphasis onto individual artworks, we find that our perception changes. This is quite obvious to many of us, of course, in this talk as people who are interested in color and light. So if we take an example of a watercolor painting, that could be medium light sensitivity. Again, the recommended illuminance level is 50 lux. In some guidance, it's 200 kilolux, some 150 kilolux a year. What if we were able to exhibit this under 30 lux? What we find is that we can reduce light energy significantly. We can prolong display duration very significantly, and the recommended maximum light exposure can also go up as well in that instance. So these numbers may or may not mean much to us here, but what they mean is basically prolonging of viewing duration and also big savings for art institutions. Moving an artwork from an exhibition space to storage and reinstating it back is often a significant cost that needs to be appreciated. Anyway, a while back, we did some experiments. This is dating back to the time before I moved to University of Sydney, where I was still at UTS. I did my PhD. We've done some experiments. We've looked at comparing our light perceptions, color perceptions, under different light level conditions. We had some 70 or so participants, ranging from 18 years old to 73 years old from memory. We tested light levels around 200 lux, all the way down to 20 lux. Now, it was quite interesting when we had people adjusted to the light levels in the space when the eye had come to that point. What we found was that while there were clearly differences between younger and older crowds in terms of their ability to distinguish colors, the ability remained consistent in a color, in an age group. So if you were in 70s, your ability to see colors under 200 lux were almost the same as your ability to see the same colors and distinguish those colors under 20 lux, as long as we gave people the right kind of environment where the contrast and glare was managed. So there is something to take away from that, I believe, where we can actually look at the minimum light levels we apply in art context, and that will mean that we can provide a lot of savings for the artwork while causing lesser damage to objects without hindering on people's enjoyment. On the contrary, to apply lower light levels, we need to think about the spaces more. We need to light them better, and that is hopefully how we will see the lighting design of art spaces evolve into the future. Now, another topic I'd like to touch on is on the relative damage sensitivity of materials. So when we look at how light causes damage to different museum objects, artworks, collections, specimens, and so on, they tend to follow this sort of a curve. So there are differences, as you can see, with different colors between different materials, but typically, as you would expect, ultraviolet portion of the spectrum causes higher, much higher degrees of damage than, say, the infrared part. So there's decline as you go to longer wavelengths in terms of damage sensitivity. So approximately, we're looking at this sort of damage response for materials. So the more bluish color of light, the more damage it will cause. And when we look at our incandescent spectral power distribution, it is more like this. So in a way, when you think about it, it's a good light source to cause lesser damage because more of the spectrum is on the warmer end of the more of the output is on the warmer end of the spectrum. Now, of course, we know that lights are evolving. Now, many of our art contexts have changed to LEDs. I didn't even talk about fluorescence and metal halides and all that used to be used in these sorts of spaces. But the point is clear. The point is that we're lighting art with different types of light, which means different degree of damage. So if you're talking about lux levels as a metric to assess light damage, then we need to compare apples for apples. And that isn't something that we are really doing now, if we honest about that. So there is already a fundamental problem about using lux to manage conservation, but I'll come to that in a moment. So the point there is, as soon as we're looking at different spectral distributions, as Rosa also went through in her talk, we're talking about not only different color perceptions, but similarly different rates of damage. And we need to basically, at the least, we need to multiply these different curves. So we are multiplying, in this instance, if it's a modern art gallery that is lit with LEDs, the red curve needs to be multiplied with the blue curve to give us the actual light damaging potential in that context. And it is interesting when we compare in this slide, if we look at the green, which is the incandescent spectrum, and the blue, which is the LED spectral distribution, we see that even though there is a bit of a blue spike in most LED products, even though that spike is evening out as we go year by year, what we find is incandescent tends to be actually more damaging to artworks in most cases because of the tiny little bit more exposure in the ultraviolet and near ultraviolet range. And as I said, it does change from material to material, but it does actually apply. And this is consistent with what Canadian Conservation Institute published a while back by comparing a whole range of light sources with one another and finding there are big differences between the range of the amount of damage that is caused by light. So we need to, again, be very conscious of what type of light we are using to really use those common practice rules quite mindfully. Now, I said using lux as a measurement method to measure light sensitivity is fundamentally quite problematic. it should be quite obvious to most people when they look at it. If you look at lux, how we measure light for our own eyes, for our own viewing, quite simply, we use a CIE standardized photopic human eye response, which basically tops at a 550 nanometers. It follows this bell curve-like context. Now, again, there's more detail to this, but quite simply just looking at a measure that is basically filtered through this lens, through the human eye and our ability to see, and applying this to measure damage that is actually caused in an exponentially reducing scale is very problematic when we think about that. So while we have all the good intentions while we're making all these calculations, measurements, and in some cases being quite pedantic about lux levels and so on, we need to think about actually the amount of unknown, amount of approximations, amount of dumbing down of the issue with that metric while we're doing all that. So in an ideal world, we would have a light meter that has this function built into it to measure damage response quite accurately. So yeah, in some ways, so this is an intentionally black slide, as some of my other intentionally black slides. If we are, again, a bit blunt, we could say we use the wrong device to make judgment about collection care. We use the wrong metric. We use a metric that leads to different outcomes depending on the type of light source we use. And on top of that, the actual science behind the classification of materials also have huge approximations that I'm sure people who are into conservation and textile and so on would know very well. So on top of that also, when we look at common practice, as we said, a lot of the time these kilolux are budgets, which have problems of their own, as we said, are also dumbed down to just lux levels, simply. So again, I guess the point I'm trying to make isn't necessarily to say what we're doing is entirely wrong. It's all, I guess, what can be done well within very limited resources and so on that many of the art institutions do struggle with. But I'd like to show you a couple more slides as we kind of look at this issue of some of the findings that we found and how these can find their way to practical application. So first, I think from that research I touched on earlier on, what we found, and there might be plus minus some changes with perhaps other sources you would find. But when we compare a standard 3000 Kelvin tungsten halogen with a UV filter, with a warm white LED, again in the 90s plus CRI or the M30, what we find is there is about 15% less damage to be caused to artworks with LEDs. That's again, on average, would mean that we could actually up light levels realistically to causing the same degree of damage. We could up the light levels, or if we were using the same light levels, we would be causing lesser damage to artworks. Again, as I said, this is very simplified. The aim here is to find ways to practically apply some of this evolving knowledge so we can progress our current guidelines. Another point with these current guidelines that we have is that there's a good research by Saunders where the total exposure limits of artworks have been discussed, where he looks at what we refer to as just noticeable fade as a measure and defines the life of an artwork in just noticeable fade. And when we normalize these, basically we can come to not only yearly exposure limits, but we can actually compare material's lifespan. So this is again somewhat complex, but when we look at it, the visual lifespan of a material in this kind of way of looking at it is measured in years. So your ISO Blue Wool scale 1 would have only 20 years if you were to light it under the proposed standards, whereas you can go all the way to thousands of years of lifespan for the Blue Wool aids. So what is interesting here is that because our art sector classifies these blue wools in 3 classifications, the same light level that we apply, let's say from Blue Wool 1 to Blue Wool 3, would cause Blue Wool 1 to last only about 20 years, whereas Blue Wool 3 will last about 200 years under those same conditions. And there is no distinction of it at this point for those who do not apply the more granular approach. So one proposed way to take the current guidelines further is this. This is what we found when we normalize the display lighting yearly total exposure limits and look at the different Blue Wools scales from 1 to 8, a bit more granular, as I said. This is the picture what we see when we apply the LED correction factor and when we apply the lifespan correction factor. We find that Blue Wool 1 would have a total overall life of 12,000 kilolux hours. Yearly total of 12 kilolux hours, and all the way down to low sensitivity, which would have practically no limit when we look at it. So if you map this to common practice in most places, again, with some exceptions, there are some quite progressive institutions. It's not to discount. We see there are some differences where we can actually reduce light levels in some instances and meaningfully light spaces. And in other cases, particularly under medium sensitivity artworks of some oil paintings and so on, we actually find that we could increase lux levels quite a lot. So if I'm sure some of the audience might be from the art world, and particularly going from Blue Wool 4 to 8, some of those numbers might look quite controversial. But really, these are just what the numbers and current metrics are telling us. Again, remembering we're using metrics that are imperfect for this purpose, but the intent remains there. So again, the difficulty is to find a balance between practice and bringing all this knowledge that has been gained by lots of different scientists and practitioners and technicians and engineers around the world. So hopefully these provide some usable and directly applicable approaches. Thank you for your time. Again, thank you to Vladi and David, and look forward to Leigh's part. Cheers.
Thank you, Emrah. Oh, this was really interesting. We now move on to our last speaker, which is Leigh Perrett. Leigh Perrett is an Australian lighting designer and audio-visual technician specializing in live performance, theatre, museum, and gallery environments. He works collaboratively with curators and exhibition teams to create immersive lighting, audio, and audio-visual experiences, utilizing his expertise in technical production, live audio, and advanced rigging. This creative practice explores visual programming and data-driven approaches to sound and lighting, and he holds a Master of Architectural Science in Illumination and a Bachelor of Creative Arts in Sound and Composition. Leigh is currently the Senior Lighting Technician at the Art Gallery of New South Wales, and he will tell us about the practical side of the artwork lighting. Leigh, are you here? Yep, over to you.
Yes, sorry, I just had a little technical glitch there. Thank you for inviting me to speak today. I feel very privileged to be speaking with such dedicated and esteemed people. And I'd just like to acknowledge them. I'm coming from Gadigal land today and pay my respects to elders past, present and emerging. So I've been in the public sector for lighting and AV for about 20 years, and working across a number of cultural institutions in that time. And so I'm not going to single out any particular cultural institution in the information that I'm going to give today. But I wanted to kind of give a more a practical approach or a practical perspective of the culture of lighting in gallery spaces and the implementation of these metrics that are given. And it's fantastic to hear the work that's being done and how we might be able to implement this moving forward. Because and I apologise, I'm going to be using examples with CRI, and I'll be using examples with lux limits to artwork, which, you know, as we can see, is they're quite flawed metrics. But these are the tools that we are working with, and I'd be, you know, really happy to get on board in changing that. But yeah, I'm going to be using those. So I want to kind of maybe give an anecdotal experience where we've had CRI issues come up. So it's not often that we get issues come up for colour rendering in the gallery space. But one particular example was we had new fixtures that we'd purchased for a exhibition, and at that, when there was a touring exhibition that came into the space, the guest curators of that space looked at the work under these spotlights that were new spots, and with new LEDs that were 95 CRI, and they said these are too vibrant. This is not what we expect from these works. The colours are too they're popping out of the works too much. And so we had to we ended up doing a combination of both wash light from a different brand of fixture. It was running a different LED, and the spotlights. We did a combination of both and balanced that vibrancy that's coming out. So I'm assuming the RG of the new LEDs was well over 100. That it was, you know, creating this vibrant experience. But yeah, the curators didn't appreciate or didn't like the colours that were being shown. It was the expectation, I think, was different for what they had. The other thing I wanted to sort of talk about is then where I've experienced in like low CRI, and a lot of fixtures that we run in galleries in Australian institutions are still probably in the mid 80s, as they're probably you know, close to 10 years old. So they, you know, as galleries try and update their equipment, I guess because of the extended lifespan of LEDs, I think we're seeing that institutions are sort of forgetting that these things need to be changed over. There's a lot of fixtures that are well over 10 years old that are still being run in institutions, which have a fairly low CRI that they've been that they sort of came onto the market in the 2010s, yeah, this is another instance where we just the culture needs to be understood, or like the what we're currently using needs to be understood better by the management system in these institutions. Another topic that I wanted to talk about was this goes back to lux levels in spaces, is white boxes and curatorial practices, where a lot of curators will, the expectation is that we have a white box galleries, and then this looking at the fact that we've got such diffuse light throughout a space in a white box gallery that it would be quite difficult to single out a particular light source on a work when the expectation is that the entire gallery space is flooded with white walls that will diffuse light all around the space. And this kind of goes back to the point of using maybe darker walls and being able to reduce light levels, in that you can then spot works and control the amount of diffuse light in a space much cleanly, and then you'd be able to practically choose the spectral output of the LEDs for individual artworks. But in sort of the cultural practice of white box spaces, I can't see that being practically implemented. So I'm just going to quickly show you a particular lamp that could be used, or like an application of being able to design an LED specific to artwork, because the practical actual application of sending a fixture with an artwork, if it was to tour, or put sending an LED chip with an artwork if it was to be displayed in other spaces, could be quite difficult. So this particular fitting is able to change out lenses, so that the lens system will come out completely, and then you've got access to the chip on board there. So you're able to disconnect the chip on board, and you would be able to swap that out. The control gear for the actual lamp is all housed in the track, which means that if you were to change the chip on board, you'd be able to change the control gear in order to drive that chip. The only factor that is sort of limiting here, it might be the information on the heat distribution within the lamp base. The lamp base itself will need to absorb and distribute enough heat to keep the LED in a balanced state. So if you were to practically design an LED specific for an artwork, if you were to need to ship either a fixture with that artwork, or you'd need to have the LED be able to be swapped in and out of fixtures such as this. However, like majority of exhibition lighting is very much integrated. So the LEDs are designed onto custom boards, and they wouldn't really be able to be removed or changed over to be made into made for a custom artwork. So the only other thing I wanted to touch on and came up with the one of the presentations is color mixing. In my experience, there are 256 steps in each color. What has not been enough to attune to what a curator would expect to be able to tune the fine detail of response, or I guess reflective response from the artwork. So I think majority of the time it's an 8-bit system that gets used in the output of each LED chip, and that allows for 255 steps. It probably would need to be like a 16-bit depth system in order to allow for enough fine tuning of each individual LED to then color match between lamps. Thank you for listening to my practical applications of these things. It's really exciting to see change in this space, and I'd really love to be implementing a new sort of cultural change to their approach to lighting.
Thank you, Leigh. Thank you so much. That was great to see the practical side of that and hear about it. You've answered quite a few questions that I had prepared throughout. So now we've finished our last presentation, and if you please have any questions, either put them in the chat or put your hand up, and we will call you out to turn on your camera and ask in person. Yeah, so while you might be putting your questions in, I just wanted to ask first, pretty much all of the speakers in regarding TM30 from the first talk. Have you, as like practicing lighting designers or dealing with the gallery artwork and museum lighting, have you used TM30 at all? Like, is there something that, because lighting designers probably know the most, apart from the manufacturers that put in their specifications, but have you ever used TM30? Was it helpful? Or Leigh, have you ever looked at that as well in the gallery, or do you only use CRI?
I think CRI is what people will recognise first in when looking to go purchases are being made, or like things are being compared when we've done analysis of like comparing fixtures for purchase. But certainly it will be pushing for TM30 to be used more often.
Mm-hmm.
Yes, the answer is yes. But yeah, as Leigh says, look, a lot of the time, the briefs you receive for a project, what people expect to hear about is CRI. So often we are at a point that, as professionals, we do consider, we look at TM30 as we look at the full spectral kind of distribution and make judgments on it, as well as actually testing and looking at different light fittings. So I think there's every indication that it will become a more widely used metric into the future.
Anyone else? Like, did you even happen to explain TM30 to anyone, like the client, for example? Like, did you ever have to go that far? No.
I guess, sorry, I jumped in, but yeah, in the case of clients in the museum and art world, some are quite, they have quite quite knowledgeable people. They understand this, even though they haven't heard of TM30. They know about the limitations of CRI and so on. I think when it's that sort of context, it's easier to have those kinds of discussions and kind of go deeper. Otherwise, I guess it will take a bit of trust on the client side that the lighting professional is doing the right thing. So often, it is guided by whether there's appetite for them to know more into the inside of what we do. I guess it applies to almost any other professional, doesn't it? So you don't always know what goes behind the scenes, but the professional is expected to apply the best knowledge available to them.
While you are unmuted, Emrah, I've got also a question for you. Have you pursued, because you did a lot of research about the light levels, even though we know Lux is not that great. Have you tried to pursue it and push for change in the museum and gallery lighting guidelines?
Yeah, interesting. First of all, I think Wenye did a lot of research. My research is more practice in practice itself and more advocation, let's say, of some of the obvious things you're talking about here in my talk. I did push in many instances quite a lot. There is always good reception and understanding of these issues, but also, I guess, conservation world is a difficult world where there's a lot of responsibility and it needs to be conservative by nature. And I think it will take many more, articles appearing on journals, research being published by, significant people, and also a few institutions taking on kind of the flagship role and changing their guidelines, which in my case, there are, I think, at least 3 significant institutions that are seriously considering these guidelines that I've just shown you, which I cannot name at the moment because they may or may not adopt them at the end. But yeah, these discussions have been happening with quite a few people, and let's see what the future looks like. Yeah.
Thank you.
I maybe can talk about some practical experience with curators and in this space. We have a lot of the time lighting is sort of considered maybe after the fact, and a common scenario for me is I have a paperwork which has been given a 50 lux limit next to an oil which is given a 200 lux limit, and I'm in a room that is white walls, and the background illuminance of the room is 70 lux, and they say light the oil and light the paperwork and make them look the same. So, well, I can't. It's more light on this piece of paper now than there should be, just for the nature of the diffuse light in the space.
If I can jump in again, I think in Leigh's work also, it will be like a lot of these decisions are governed by loan agreements and so on. So there's only that much freedom as to what you can do, especially if it's a traveling exhibition and what can be done. So even if the institution might be very progressive and innovative, they still need to apply the contracts that they've signed up to when they are receiving artworks and putting them on display. Quite complex. Yeah.
Do the contracts actually talk about, sorry, Rosa, do the contracts actually talk about the color of the space, for example, that it needs to be displayed? Because like summarizing all what Leigh was saying and Wenye's interesting research and Emrah's talk, if we were able to maybe have dark spaces where we can adjust the lighting exactly for each art piece rather than flush diffuse lighting the whole space, that would help save and protect the artwork and also utilize the lighting in the way that we can actually support that, have the spectra adjusted and similar things.
Yeah, 100%. I every time I have go into a meeting where a new exhibition is being presented and they say, this one we're going to have like dark walls, I'm cheering. I'm very, very excited because I can now actually implement much more control over in the space, and we can bring the light levels down while still maintaining visual acuity. One other thing that I didn't sort of touch on, and leads into this a little bit, is coloured walls. A lot of practice at the moment is going into these very vibrant coloured walls in spaces, which might saturate your cones, and then you're visually seeing works differently, but that's really not considered. So that's a little side tangent.
Rosa, you had a question?
No, I didn't. No, good.
Yeah, because that was actually the other thought that I had when I was listening to Wenye's talk, because how would that deal with how would such a light source deal with for example, colored walls? How would such a light pick up, a wall of color that is not supported in the spectra, or is dimmed in the spectra, for example, or whether, you have heard of.
Yeah, I think at one point, like on my slides, I mentioned a little bit in the lighting design part. We hope the lighting design is a kind of perceptually driven lighting design, not just the number, the illuminance itself. We also need to consider the space. Like the color of the wall, the different color will definitely change our color perception of the paintings, of the artwork itself, because our visual system not just pick up a kind of absolute value or like the absolute color. We keep doing the comparison, and our eyes, our brain just pick up the difference between the artwork and also the background. So both the brightness and also the color of the background will impact our color perception. And sometimes in the museum, when we move from, let's say, the outdoor environment into the museum, our previous exposure history under the daylight will also change our perception. So in the lighting environment, we probably need to design something kind of step by step and help people get adapted to the lighting environment. But of course, just like Emrah and Leigh said, it's just kind of our lighting people's wish. And it depends on how our client and also the owner recognize the importance of lighting. I think it's not just happened in the museum lighting, it just happened generally for all the architectural lighting, like how interior designer and architects believe lighting is important for their project, and how much support they can give us. Not give us like a very limited environment and ask us to do a good lighting design. It's not sufficient. We need their support to change maybe the background for us. I think I probably asked too much as a lighting people.
If I jump in again in case there are no other questions so far. So I think it's interesting when you talk about Vladi, like whether when you have a contract to light a certain collection in a certain way and so on. It's similar to a contract where you light a building, light a room, light a project, where what I find is like a lot of the time the difference between good outcomes and excellent outcomes is that those excellent ones are where the rules are bent, the environment where the technician, the designer is working allows for those kind of initiatives and those kind of risks to be taken. And often actually some of the award-winning lighting projects are actually, they have a lot of non-compliances with contracts and so on, but nobody cares about those things because it actually works. You know, it's a good outcome and the standard becomes irrelevant. So there are examples of exhibitions where I guess the loan agreements are, you know, to some extent very cautiously put aside for an amazing outcome that goes beyond what people expect. But it's rare. Yeah.
Thank you. Yeah,
I think we have a question in the chat box.
Yeah, there is a question. I don't know if it's quite related to the topic. It's asking whether the lighting seems to aim for purity. It's from Josefina. For purity of lighting, whereas she thinks it's sometimes used for emotional effect or even manipulation. And then she's asking for any comment. It's general question for lighting, I think, not for artwork lighting.
Yeah,
Maybe
sorry, you're gonna
after
you go, Wenye, please.
Okay, maybe my thoughts for this question at the first is it depends on if we are talking about the color of the lighting itself, or we talk about the color of those artwork, or maybe the object color. Because in the museum we probably only use the white light, even just maybe enhance the color a little bit, but we will never use a very colorful light in the museum. In some scenario, maybe in a restaurant or hospitality applications, we do use colored light to impact the emotion. We also try to see if we can use a color of light to manipulate people's emotion in the aged care center, like to make those senior person more engaged into the environment. And if we are talking about the color of the painting, so in the museum, we probably just use white light to represent the true color of the painting itself. Some artists like Picasso, they tend to use very strong color to express the emotion. I remember there was a painting called Tragedy, I think, which is a very famous painting for his blue period, because at one point he created a lot of blue background painting and to show the sadness. So it depends on the color of the light or the color of the painting or color of the objects. Yeah, Emrah.
Yeah, thank you. Yeah, I guess, you know, almost all of us have been quite clinical and kind of technical in our kind of approach as far as these talks are concerned. But yeah, I guess to Josephine's question there, it's at the end of the day, the designer, the technician would be guided by the curator's overall vision and the story, or the artwork's, you know, story. So there are different approaches that you can apply with, of course. There are cases where I remember one distinct example in an exhibition in Barcelona where I think it was a Rembrandt exhibition, if I'm not wrong, where the room was entirely darkened, the artworks were framed, and there were additional lighting effects into the room as if the light was coming through a window in the painting itself, and, you know, shedding onto a corner of a room of the actual space. So there's so much that can be done by manipulating the space, you know, conveying emotion and kind of making it more immersive. And of course, with the digital technologies and controls, smart controls we have now, it's endless. But I guess, yeah, the lighting, the role for the lighting person often is being a translator between what is the story, what's the message, what's the angle that is being looked at, and how do we translate it to a technical outcome.
Yeah, I'm seeing a increase over the decades of a approach to exhibition spaces that are more almost theatrical, and thinking about the experience as walking into a space that to have feeling that not just from looking at the details of the artwork, but having an experience that integrates vision and lighting and sound with with the visual works, that to give a more richer surroundings and a more richer experience. Yeah.
Yeah, I was just going to say exactly what Leigh is saying. I think it depends. Yeah, Josephine, it depends. For us, it depends on the project really. Some projects are to the brief is just to purely perhaps to tick all the boxes so that the light almost comes unnoticed and you just see the artwork and you don't notice the lighting. And maybe some other projects can be completely the opposite, where the light is actually a big part of the project and is intentionally changing your perception and how you perceive and what do you feel, and each room might be completely different and call for different emotions. So it really depends. I think lighting is so wonderful in that sense that that you can pretty much do anything with it. Depends how you use it.
Thank you. Josephine says, Leigh, yes, the lady and the unicorn exhibition, very moody space, a rich experience. True. Thank you. So do we have any other more questions? I've exhausted mine. Looks like there's no more questions. So I would hand over to David now to conclude the event for us, please.
Okay. I think hopefully you can see me there. Thank you so much, everyone. That was just brilliant. Every presentation, and it'll be on our Colour Society of Australia YouTube channel. So I think that'll be a great source of information for years to come. And thank you, Vladi, for doing such a great job with the presentation. I think we should make you our permanent host of our webinars from now on.
Thank you.
Yes, no, absolutely brilliant. All right, well, thanks everyone. I guess it's just for me to thank our speakers and our attendees for their attention. All right.
Thank you so much.
Thanks everyone.
Thank you. Have a great evening, morning.
Thank you.
Bye.
Thank you.